Okay, it works. Stick it to yourself somewhere. I think it's great to use your pocket. Or
Yeah, maybe say, you know what, I have this junk in my pocket, so I need this one. You need most of it. And then it will be easier, yeah?
Yeah, you can actually stick it from outside, but it doesn't matter.
Yeah, well, I mean, if it doesn't matter, it's okay.
Now it's this way.
Okay.
Yeah, well, I'm trying to say something. Yeah. I guess it works. Okay, good.
we welcome you here in Northern part of Ostrava. Now we are, after the competition, you are without stress. I hope that the competition problems with you well and that you have solved them successfully. I also hope that you enjoy your stay in Ostrava. And in order to enjoy it a little bit more, we prepared for you two nice lectures. The first lecture is by Professor Pavel Glavský from the Mathematical Institute of the University of Katowice, and he will tell us something about functions which are not functions.
Yeah, that's right. So thank you for the introduction, and thank you for the organizers for inviting me. It's it's a big pleasure to be here in Ostrava again, and in particular to give this lecture as a part of the Wojtek Jardik competition, which I was actually participating myself, 20 years ago when I was a student. So it also brings some nice memories. And it's particularly nice to be able to give a talk here and maybe grow your interest in some parts of mathematics that are relevant to what I'm doing. So the title of the talk, of the first talk for today, is what if one-to-one functions aren't really functions? So it's it looks a little bit mysterious. I mean, it's almost as if asking, what if one is not one? But I will quickly try to explain what it means. So basically, we all know the definition of a function which is one-to-one. We all know the definition of injective function, and this is something that we basically learned already in high school. We say that a function is one-to-one if it carries different arguments into different values. So basically, a function is one-to-one if we take two elements, x and y, and they are different, then f of x is different from f of y. So what does it have to do with the initial question? What if functions are not functions? Well, we will try to generalize the concept of this one-to-one function to some more general objects which are not necessarily functions. So the ones which are not necessarily functions between two sets. Would it be possible to define the notion of something which is injective, something which is one-to-one in this more general context? And of course it is possible, and we somehow know how it works. So basically, if we decide to define one-to-one functions which are not functions, well, the first obstacle to overcome is to make sure that we are not necessarily working in the realm of sets. So this definition is okay. I mean, it's a proper definition. But the main or the first obstacle in generalizing it to a more broader setting is that it relies on the fact that x and y are sets, and it refers specifically to the elements of those sets. We specifically point to elements x and y of some given sets. So if we try to advance to the situation when this is some mapping between objects which are not necessarily sets, well, we have to get rid of this assumption. And at first thought, it seems to be fairly easy, and again, it somehow goes back to high school mathematics. Namely, we learn at some point of our education that if a function is one-to-one, well, that basically means that we can construct the inverse function to this given function f. It seems to be a good candidate for generalizing the definition of injective function. well, we just say that function will be injective, or this mapping or this whatever we are going to create will be injective if it will be possible to pick an inverse mapping going the other direction. Well, it's more or less okay. This fact is widely known, but if we try to prove it, it's also not particularly complicated. You know, if we decided to prove something like that, one way is fairly easy. I mean, if we have some left inverse to a given function f, so if we have some function g from y to x such that g composed with f is the identity on function on the set x, well, how do we show that f is injective? Well, it's pretty straightforward. Yeah, I mean, let's say that f of x1 is equal to f of x2. Well, if we just take the image of those two elements, or this one element via a g, well, we get that this is g of f of x1, while this is g of f of x2. Well, these two compose to identity, so this is just x1, well, this is just x2. Well, so there we go, x1 is equal to x2. Well, the other way is also not difficult to show. I mean, it's very natural. So let's say that f is injective. And let's try to show that we have this left inverse. Well, I mean, it's almost straightforward. So you know, for every element y in capital Y, if y is in the image of x with respect to f, well, then there exists exactly one element x in x, which is carried onto y. And of course, if y is not in the image of f of x, you know, we can pick some arbitrary element x0 in x, and then we can define this inverse function. So then we can define g of y to be equal x if y is in f of x, and f of x is equal to y, or we can just say that this is x0 if y is not in f of x. So this is a well-defined function. Because f is injective, this point x is uniquely chosen, so it definitely is a function. And you know, from the construction, it follows that g composed with f is identity on x. So everything checks, and it seems to be a good idea to accept this this theorem or this proposition as a new definition of injectivity. There's one problem, however. If we are talking about functions which are injective, or one-to-one functions, we somehow have this dual notion of functions which are surjective, of functions which are onto. So we would also want to have a corresponding result for functions which are surjective. So, you know, our classical definition is the following one: a function is surjective if for every element of the counter domain we are able to pick something from the domain such that this is the image of this element. Well, but again, we don't like it because we have to specifically refer to the fact that X and Y are sets, and we have to pick some elements of those sets. So we would also want to generalize it to a different setting where we not necessarily work with sets and functions. So, you know, if that was our definition of, if that was our candidate for the new definition of injective function, it seems a natural. It seems like a natural idea to define functions which would be surjective as such that have the right inverse. Well, it seems to be working. Again, if we decided to have a look at the proof of this theorem, which again is not complicated, we can go through it real fast. What will happen? Well, one way, I mean, this way is really pretty straightforward. So if F composed with G is just the identity on the set Y, that essentially means that for every element Y in Y, F composed with G of Y is equal to Y. So for every element Y in Y, there's an element X in X, namely X equal G of Y, such that F of X is equal to Y. So there's really nothing to show here. So let's try to see what happens if you go the other way. So let's assume that F is surjective. And let's try to construct this function G that would go from Y to X and would be the right inverse of F. Well, I mean, again, well, the concept is fairly easy because this function is surjective. While for every element of the set Y, we are able to find something from the counter image of this function. So basically, if we want to define a function that goes from Y to X, well, we have to define a value for this function G for every element of the set capital Y. So for every element Y from the capital Y, the counter image with respect to this element Y is clearly not empty. So for every element Y in Y, we can pick some element, let's call it Yx in F inverse of Y, and then defining function G is fairly obvious. G of Y is just this element Yx. Okay, so we have a proof, but what is suspicious about this proof? What's wrong with this reasoning? Well, there's nothing wrong with it, but at this stage, right here in this step, you've probably noticed that we are using axiom of choice. So, well, not everybody likes axiom of choice, and there's a reason for that. I mean, if we somehow want to approach mathematics from the constructive side, we sort of want to get rid of all the reasonings that involve the use of axiom of choice. So maybe this definition or this way of generalizing inverse function, the definition of in this particular case, surjective functions to this setting, well, maybe this particular way is not optimal. Maybe we can do better than this because, well, we have to use the axiom of choice to construct this inverse function G. So maybe there's another way to do that. And yeah, sure enough, there is one. It will have to have something to do with those left and right inverses. what is the intuition behind all of that? Why do we really want to be able to invert functions or invert elements in groups or rings or whatever algebras? Well, essentially to be able to solve equations or at least cancel terms. And we know that well, the property of cancellation is in general weaker than the property of inverting elements, but maybe it's enough. So maybe it's enough to define functions which are supposed to be the generalized injective functions, as such for which some sort of cancellation property holds, instead of having these inverse elements. And well, I already mentioned that we are using the axiom of choice, and the idea is the following one. So let's try to accept the following cancellation law for our alternate definition of injectivity or surjectivity. So first of all, we will say that the function is injective if for any other set and for any other functions g1, g2 going from this set to the domain of our function, while if this composition f with g1 and f with g2 agree, it automatically follows that we can cancel f and just imply that g1 is equal to g2. And then the dual notion, or the surjectivity, would be very similar. We just have to look at functions g1 and g2 that go from the counter domain to some additional set z, and basically cancel f from the other side. Well, first of all, let's check that this is correct, and that this actually gives us a good characterization of injective and surjective functions. So let's try with the injectivity function, with injectivity first. So, well, let's try to go this way first. So let's say that the function f from x to y is injective. And we want to show this cancellation property, that it actually holds. So, just fix some set w and some functions g1 and g2 that go from w to x, such that, well, f composed with g1 is the same thing as f composed with g2. And of course, the question is, well, is it true that g1 is equal to g2? Well, so basically we have to make sure that they agree on all values. Yeah, but of course they do. If we fix some element w in capital W, what happens is that f of g1 of w is equal to f of g2 of w, but well, f is injective, so if it agrees on those 2 points, that means that they have to be equal. So g1 of w is equal to g2 of w, which is exactly what we wanted to show. Well, how about the other way around? How about proving that if we have a function that satisfies this cancellation property, then we are able to deduce that this function is necessarily injective. It's necessarily one-to-one. Okay, well, so suppose that for all sets w and for all functions g1, g2 that go from w to x, if f composed with g1 is the same thing as f composed with g2, then necessarily g1 is equal to g2. And well, the question is it true that F is injective? All right, so let's see. So let's take some two elements of X. So let's say that we have some elements x1 and x2 in capital X, and such that f of x1 is equal to f of x2. So how can we use this property? Well, I mean, it's it's a common trick. This thing works for any set W and any functions g1 and g2 that go from W to X. So let's just take, well, any set, any singleton set W consisting of only one element W, and let's define two functions g1 and g2 which work as follows. Well, g1 maps this element W on x1, and g2 maps W on x2. All right. So yeah, so these are perfectly well-defined functions. Everything is okay so far. So what is F composed with g1 of W? Well, this is just F of g1 of W. Well, g1 of W is x1, so this is just F of x1, which is the same thing as F of x2. And then we can basically fold the same reasoning the other direction, so that will be the same thing as F composed with g2 of W. Well, so in particular, F composed with g1 is the same thing as F composed with g2, because we only have to compare one element for a singleton set. So that basically means that g1, that basically means that g1 is the same thing as g2. So in particular, g1 of W is equal to g2 of W. Well, but that was x1, and this is x2. So we have that x1 is equal to x2, end of the proof. Well, how about surjectivity? Well, again, one way is almost straightforward. So basically showing that if function is surjective, then we have this cancellation property. Well, yeah, I mean, it would be sort of boring to go through it in all details, but this is easy. Well, I mean, if function is surjective, well, you have to show something like that. Well, but it works. Yeah, I mean, basically for any element from Y, you can pick some element from X, such that Y is equal to F of X. So if this holds, well, then it means that you can compare values of G1 and G2 for every single element of Y. So this is really easy. I mean, let's don't waste time on this. The other way, well, the other way is not hard either, but it maybe requires some argument. So if we try to show the other direction, if we want to show the other direction, well, let's assume that we have this cancellation property. So for all sets Z and for all functions G1 and G2 that go from Y to Z, if G1 composed with F is the same thing as G2 composed with F, then necessarily G1 is equal to G2. And we are asking if F is surjective. So what can we do? Well, the usual way of proving theorems that we don't know how to start is, well, let's try to go by contradiction. So suppose that there is some element, well, let's call it y0 in y, such that for all x in x, f of x is different from y0. Okay, so now we have this property for all functions g1 and g2. So let's try to somehow use it to get a contradiction. For a set Z, consider the set Y union, well, a singleton set consisting of Y. And let's define functions g1 and g2 as follows. So g1 of y will be just f. Let's see, so that I don't get lost. G1 of y. Well, let's just say this will be just y. And g2 of y will be equal to well, I have to write it down in a smart way. Yeah, it would be y if y is different from this y0, or the whole set y, which is really a separate element of z, if y was equal to y0. So what happens now? So G1 composed with f on any element of x is what? Well, it's just G1 of f of x. So this is just f of x. And G2 composed with f of x is just G2 of f of x. Well, but this is never equal to y0, so this is also f of x. Well, so these two things are always equal, which follows that G1 is the same function as G2. Well, but of course it's not, because G1 of y0 is y0, and G2 of y0 is, well, the whole set y. So we have a contradiction here. So, well, I mean, it's not difficult to prove those theorems. I mean, if you somehow figure out those two tricks to showing that either one of those cancellation properties implies injectivity or surjectivity, well, the reasoning is really fairly easy. So it seems that we have a good characterization of injectivity and surjectivity that works for functions for sets. And well, even though those proofs were not complicated, I still somehow insisted on showing you all the details. Well, just to make sure that that I convince you that there's nothing suspicious with those proofs. So, for example, we don't use any arguments that would require axiom of choice, or other methods that would be otherwise controversial for one reason or another. So there's really nothing that can go wrong, and no reasons for anybody to be critical about those proofs and choosing this particular characterization for injectivity and surjectivity. Okay, well, so yeah, so we have a good idea for well, defining injective or surjective functions without actually referring to the fact that, well, they are functions on sets. But why do we want to do this in the first place? That was maybe the fundamental question that we should have answered at the beginning. Well, basically, the reason is because we want to talk about well, mappings between objects in a much broader sense, and basically this is because we want to discuss a concept which is called a category in mathematics. So what is a category? Well, very roughly speaking, well, category is a data that consists of two entities, of objects and arrows, which are also called morphisms, which satisfy certain properties, and I gave you well, the exact definition on this slide. They are very natural objects. I mean, the concept is very natural. So we are looking at a class of some objects, and to begin with, let's just try to think about some simple example. So we start with thinking about a category of, let's say, sets. So objects of our category are sets. Set X, set Y, set Z, and so on and so on. And together with those objects, we also define some mappings between those objects. So essentially, for every two objects, we consider the set that we denote by hom of xy, which is assigned to any disjoint pair of objects. And an element of this set will be called a morphism, or an arrow, which is maybe a better name if you somehow want to free yourself from this way of thinking of morphisms as functions, and will be denoted basically by the function symbol. And together with the operation of composing two arrows, which very much resembles the concept of composition of two functions. So basically, if we have three objects, x, y, and z in our category, while a composition of functions, well, it's again, a composition of morphisms is a function between, actually maybe a better name than a function is a binary operation on those sets of morphisms, which to two morphisms, one going from x to y and another one going from y to z, assigns a new morphism that goes from x to z, which satisfies some very, very natural properties. So first of all, we want to make sure that this composition of morphisms is associative, so that H composed with G of F is the same thing as H of G composed with F, and such that this particular morphism assigned to every object of which we think as identity morphism behaves in the way that identity behaves. So basically, composing anything with identity doesn't do anything. So if we have two morphisms, one going to y and one going out of y, and we consider identity on y, no matter in which order you compose, it doesn't change anything. So this is the most general definition of a category. There are some issues with this language that I use for this slide. For example, somebody who is really picky might question why we call this composition of morphism a function, while maybe all those hom sets, so all those collections of arrows between two objects, are not sets, and it doesn't really make sense to speak about a function in this context. But let's just put it aside and let's just don't go into too many details. You can probably guess that it can be relatively easily generalized to the concept when we don't necessarily have to talk about functions. We might as well call them relations, and it would work as well. But it's maybe just easier to use this language that we are used to, just to explain the general concept. Okay, so what are examples of categories? Well, everything you have learned so far in mathematics is basically some sort of a category, and some of those examples are fairly obvious, some of them are really quite apparent, and some of them are maybe not so obvious. But you will see that, well, even though they are maybe not so obvious, but they are still quite useful. So, examples of categories. Well, the category set. So, objects, well, are just functions. Function sets, of course, yeah. Morphisms or arrows are functions. So this is the most canonical example you can think of. We can look at the category of sets well, objects in this category are just the usual sets, and arrows between objects are functions. So we have some objects denoted x, y, and z, while and the usual functions between those sets that play the role of what we call arrows. And in particular, in this case, if we want to somehow define arrows that would be monomorphisms, while we can use our proper definition of arrows which are, well, satisfying this cancellation property. So basically, an arrow f would be injective, or would be a mono if for every object w and for every maps well, G1 and G2 that go from W to X, while F composed with G1 equal F composed with G2 would imply G1 equal to G2, and a similar concept for functions that are surjective. But of course, and we have just proven that half an hour ago, for this particular category, well, this means nothing else but to require that the function f is injective in the usual case. Well, then, of course, is the whole bunch of other familiar examples from standard courses in mathematics. So, well, the category GRP, whose objects are groups and morphisms, are actually, well, group homomorphisms. Well, similar thing, and we also remember that we have, well, more specific characterizations of morphisms which are injective in this particular category. So, for example, we can say that something is injective if and only if, well, the kernel is a singleton. It only consists of the neutral element of one group. But anyways, groups, well, they form a category. Arrows or morphisms are just the usual group homomorphisms. Well, similar thing goes for abelian groups. Or for rings, or for modules over a fixed ring, or if you don't like modules, well, might as well take vector spaces over a fixed field. So all those familiar algebraic objects that we know, well, they are always examples of some category with very natural description of morphisms as those maps that appear in our setting. Well, it just happens so that all those examples that I listed here, they are somehow connected to algebra. Well, the reason being that I mostly work in algebra, but of course that's not the case at all. You know, the category top of all topological spaces with morphisms being just continuous maps. Well, that's, let's say, at least one example somehow from outside of algebra. But really, you can think about just about any category of mathematical objects that you have studied so far with respective maps between those objects. And I guarantee you that you will always get an example of some sort of a category. Well, however, in all those examples listed here, well, we don't really need to worry about this fancy stuff because, well, all functions, all morphisms here are functions. I mean, well, group homomorphism is a function. You know, well, the continuous function is a function, or a continuous map is a function. So we don't really need to worry about objects not being sets because it doesn't happen here. So is it just, does it really make sense to introduce those generalized notions for monomorphisms or epimorphisms because we don't really need them in those examples? Well, needless to say, we are not restricting ourselves just to the case when we are dealing with categories whose objects are sets and whose morphisms are functions. And obviously, whenever somebody starts talking about examples of whatever entities which are not sets, well, everybody gets scared and starts thinking about whatever proper classes or some sophisticated constructions from set theory. No, we don't have to do that. I mean, the examples are very similar. Very, very simple. Well, for example, let's take a partial order on a given set. So this is a partial order. On some non-empty set P. So you know a binary relation which is, well, whatever it is, reflexive and asymmetric and transitive. Well, this is actually a category. Why is that? Well, objects are elements of P. Well, how about arrows or morphisms? Well, if we have two elements of this set P, which are in a relation with each other, so if we have some element A and B, and we can say that A is less or equal than B, well, by definition, we can also declare an arrow that goes from A to B. So basically, we can draw the diagram of this relation. Well, if it's a partial order, it always looks well, yeah, it's well, there's lots of partial orders. Let's say something like that. Well, this is actually an example of a category. And, well, it's not complicated. I mean, it's very natural. We come across partial orders just about everywhere in mathematics. Objects of this category are not sets. They are elements of this set P. So, but they are not sets themselves. Yeah, I mean, of course, you can come up with some set theoretical constructions so that you could think about those as sets, but they are not sets in the in a common meaning of what we mean by sets. They are just some points on the plane in the graph of this relation. And arrows, well, those morphisms in our category, well, they are not functions. Yeah, I mean, they somehow relate to this relation of partial ordering, but you cannot say that we have a function from this point to that one. Well, because that wouldn't really make much sense. Well, of course, you can always somehow adjust setting to be able to define some functions within that graph, but that's not the point. I mean, the natural way to look at it is that we just have some arrows between points, and we declare those arrows to be our morphisms. So this is a perfect example of a category whose objects are not sets and whose arrows are in particular not functions. And actually verifying that this this list of axioms is satisfied, well, I mean, it's almost trivial. Yeah, I mean, really, all we have to check is that composition of arrows is associative. So that if we if we compare different elements, it doesn't really matter in which order we compare them. But this is pretty much straightforward. I mean, it follows from the fact that the relation of partial ordering is transitive. So checking that the definition agrees is fairly easy. Okay, well, so partial orders work. We don't have to restrict to partial orders. We can basically look at any graph. Directed graph. Yeah. So, we can think about some directed graph of some sort, which is not a partial order. So, basically the main difference is that it can also go into circles. So we can arrange for those arrows so that they behave in a nasty way. You can just draw here whatever you want. Let's say something like that, and from here over here. That would be also example of a category. So again, vertices, objects are vertices. And arrows are those directed edges. Again, it's almost obvious to see that this definition is satisfied. While it's the way we structure this directed graph is clearly much more general than the restrictive definition of a partial order. So we can really draw whatever we want, and we will still get an example of a category. So we have this example as well. Of course, you can really go almost everywhere from this direction. So we can also define or give an example of a category. The category cat. well, doesn't really have much to do with cats, but objects are categories. And arrows, well, what are arrows then? Well, arrows are what we call functors. And functors are essentially maps between two categories. So a functor between a category C and a category D, well, it's an assignment. I don't really want to use the name function. It's an assignment that assigns both objects from D to objects from X, and morphisms from D to morphisms from C, such that certain natural axioms are satisfied. I mean, it would be sort of pointless to list them. But anyways, you know, this is just, well, as you can guess, a functor, a map between two categories, is something that assigns objects of one category to objects to another category, and morphisms of one category to morphisms of another category. So so actually, while you can build new categories from already existing categories, and consider functors between categories as arrows in this new category. And with this concept, at this level of generality, well, you can define pretty much everything if you just adjust your language carefully. So, for example, let's say that we have a category of sets, and then we have a category consisting of two objects and one arrow between those two objects. Well, we want to define a functor that goes from this category to the category of sets. Well, what is it? What is this functor? Well, basically, this arrow tells us, well, you can think about it as some form of a partial ordering. So this one particular arrow tells you that this element is first, and this element is the second one. And now you have an assignment from this concept to the concept of sets, to the category of sets. So basically, well, you can somehow marry two worlds. Well, you can somehow say which object will be the first one, which one will be the second one, when the underlying objects will be sets. So this is, very roughly speaking, this functor corresponds to the idea of ordered ordered pair of sets, well, which is just you know, the binary Cartesian product. So from today, well, you know, just don't think about binary products as some whatever ordered pairs of elements. An ordered pair of sets, or really a binary product of sets, is really nothing else but a functor from the index category consisting of two elements to the category of sets. Now, this might look strange if you see it for the first time, but just wait till you start learning algebraic geometry or algebraic topology. This is really the commonly used language these days, and by these days, I mean everything that started from late 1960s. Really, if you look in any more advanced textbook on, let's say, algebraic geometry, but also algebraic topology, well, all all those concepts that that grew from, let's say, Grothendieck school, you will see that they don't even bother with providing elementary definitions, whatever it would mean, elementary. Well, when you speak about schemes or sheaves or whatever push-outs, well, you don't bother in explaining that these are some sorts of ordered pairs that satisfy some extra properties. Well, you just say that this is a functor from one index category to some other category, and everybody knows what it means. So yeah, so basically, you know, we started with considering well, one-to-one functions which are not really functions, and then we were sort of thinking, okay, so how can we modify this definition that we get equivalent concept for sets, but one that will be still useful in more general setting. And we essentially arrived to the concept of a category and functors between categories. Well, I encourage you to learn a little bit more about this, and hopefully you will get interested in some of those concepts of category theory after that talk. And really, just, you know, learn some of this stuff because it will make your life easier, and it will also give you, well, maybe a broader perspective on mathematics and well, on different ways of defining things in mathematics. So, well, thank you very much for your attention, and well, if you have any questions, feel free to ask. Yeah.
I would like to thank Pavel for his very nice lecture full of arrows. Do you have some questions or comments? Or arrows? Yeah, okay.
Mm-hmm.
Necessary to map the arrow between 2 points onto map between the two objects, the two images.
But in which part you mean?
Yeah, for example, in the very top one,
Uh-huh.
whether we can't map the 2 points on some two objects, two sets,
Mm-hmm.
the arrow to some other function
Yeah.
between the two sets. Whether it is So our next speaker is Professor Vilém Novák from the Institute of Research and Applications of Fuzzy Modeling from Ostrava, and he will tell us something about vagueness.
So, good afternoon, ladies and gentlemen. My talk will be not purely mathematical, but also philosophical, and I will especially focus on mathematical model of so-called vagueness phenomenon. Where does it come from? What does it mean? I think everybody knows probability theory, and which is say mathematization of uncertainty. And this uncertainty comes when we are realizing a sort of experiment, whatever kind it is, which can have several outcomes. Then we don't have enough information about which outcome will appear. And therefore, the probability theory is a mathematical model how to supply a certain information about specific outcomes of a given experiment, whether they come and how likely they should come. Vagueness is a different phenomenon. Vagueness is a phenomenon which appears in human mind, especially when thinking and when using natural language. And using natural language, we use expressions like young lady, old man, deep sea, beautiful, beautiful town or something like that. And if we are thinking, what does it mean, for example, a young man, how old is young man, we come to the problems. And we meet the phenomenon which is called vagueness. And the question is, how can we model vagueness? It can be demonstrated, and it was demonstrated that probability theory is not proper theory for modeling vagueness. And there is another theory, especially here you can see fuzzy logic. I will speak about it also, but I will speak about sources of vagueness. There is a man who has very nice hair, so my question is, are you bald? No. And how do you know that you are not bald? How do you know that you have more than 0 hair? Yeah. Okay, so if you are not bald, it means that you have many hair, and that the number of hair, it can be something around 70,000 or 100,000 hair, means that you are not bald. At any case, I can give you proof that you are bald. And this proof comes already from old Greeks. Eubulides from Miletus, 4th century before Christus. He came, he was famous with, he called them puzzles. And 2 of his famous puzzles are Phalacros and also Sorites paradox. Here is this paradox. A man with no hair is bald. A man with 1 hair more than a bald man is still bald, and consequently, all men are bald. This can be proved. Here is a proof, a very simple one. If 0 hair means bald, and having 0 hair is bald, then also having only 1 hair on the head is bald, then using the rule of modus ponens, we conclude that also a man having 1 hair is bald, and so on. So finally, we come to the conclusion, after finite steps, that somebody who has 70,000 hair is bald. We can also exactly the same in a sense is the Sorites paradox of heaps. So here you can read it, 1 grain doesn't make a heap. Adding 1 grain to what is not yet a heap doesn't make a heap. Consequently, there are no heaps. We can also prove that everybody is bald using induction, mathematical induction. Let us consider a set of all numbers, finite numbers, which mean that this number of hair is bald. And then, because 0 belongs to this set, and we know that if n belongs to this set, then n plus 1 also belongs to this set, then by induction principle, we conclude that this set of natural numbers is equal to the set of all natural numbers. And consequently, all people are bald. So everybody here, including me, are bald. Though everybody knows that he or she is not bald. So this is strange. And what we conclude that there are properties for which the induction principle fails. So classical mathematical induction cannot be used wherever you think it could be used. And the main problem is in this implication. So for all n, if n means bold, then n plus 1 is bold. Is such an implication true? I think it is not true. The problem is simply that somehow the shape of head changes if there is one hair more than 0, or I don't know how many, say 100, so 101, that means that this man or woman is different, has a different head than the previous one. But here we have no other choice because we are using classical logic. So this is related to the vagueness. So these paradoxes of Sorites or paradox of Phalacros, hips and bald men, are most essential properties which accompany the phenomenon of vagueness. And so vagueness raises if we try to group together objects that have a certain property. And we can consider actualized grouping of objects. It means actualized means that all objects are, at least in our mind, at one moment at disposal. This grouping of objects cannot be taken as a set because it can be vaguely delineated, and this is given by the character of the given property. There are for sure typical objects, we call them prototypes. And so these are objects which surely have the given property phi. And there surely are objects which don't have property phi. It is your case that you are not bald because you have more than 0 hair. And this is essential. There are also borderline objects. It is unclear whether they have the property phi or not. If we simply add hair one by one, so 100 from the small distance, such a man is still a sort of bald. But if he or she has, say, 20,000 hair, I'm not sure whether he is bald or not. And there is also one essential property which can be called continuity. This property of vagueness has been recognized already by English philosopher Max Black in 1937. And he speaks about something like museum of applied logic. Imagine, I repeat his example, imagine that you have a chair made of wood. And then you are trying to cut arbitrary small pieces of this chair. And at each moment after I cut some small piece, I ask you, is it a chair or not? And you all, in the beginning, it is easy, but still continuing this procedure, it will be more and more difficult. And after some moment, you realize that you say, this is a chair, but it will be some piece of wood without any form, so for sure it is not a chair. Simply, you didn't recognize the moment when the chair ceased to be chair. And this is typical. Simply, there is no abrupt change from having the property or not having the property phi. So this is, you are running through borderline objects, and you suddenly come from phi to not phi, and you don't know when. You cannot determine that. So now the question is how to model such a phenomenon. There are, at least known to me, two essential and beautiful models of that. The first is the notion of so-called semiset. I will speak about it later on, so not now. And now I speak about another concept that this is called fuzzy set. I think you know about this, you have heard about it. It was established by American professor Lotfi Zadeh in 1965. And his idea is very simple. If we have a universe U, then we consider a function which from U to interval 0, 1. And this interval 0, 1 can be understood as a set of degrees of truth. So if we are given an element from the universe U, then the value from 0, 1, it means functional value of this function, is a degree of truth that the element X has the given property denoted by this capital A. if you look at it, it is easy to see that it is a generalization of the standard characteristic function of a set. And here is a picture. So, for example, speaking about bald or small people or whatever, in fact, this is a function of this shape. Here are numbers of hair, and there are some numbers for which we for sure know that they mean to bald. I wrote here, for example, 100, something like that. And then, so these are kernel objects. These are objects which for sure have the property, in this case, to be bald. And here are the objects, objects which are borderline, for which it is not completely clear whether they are bald or not. And here are objects, it means numbers, which for sure don't have the given property. So I think this is quite clear. Here is another example for small people. For example, we know that the smallest consider adult people. The smallest man, or I don't know, woman, had something like 40 centimeters. The tallest thinkable people have 220 centimeters. So the kernel people, which for sure are small, so up to, say, 165. And then there are borderline people of the height of these people, and it is finished something before 180. So this is a fuzzy set. And another I will return to this later on when speaking about fuzzy logic. And now let me mention the so-called alternative set theory. Alternative set theory was established by Czech mathematician Peter Vopienka, who unfortunately died 4 years ago. And he proclaimed the following sentence, that mathematics uses infinity whenever it faces vagueness. It is somehow surprising, and I will try to demonstrate that his idea is really very true. And what he introduced in this alternative set theory is a different understanding to infinity. What is infinity? He calls this, or he called this natural infinity. So, what is the source of natural infinity? Consider the number 10 to 120. And imagine that we, by computer or whatever, will be counting each second 10 to 12 atoms. So 1, 2, 3, 4, 5, and so on. And we finish with 10 to 12 after 1 second. And then if we do it and count each second 10 to 12 atoms, then it would take us 10 to 100 years. Which is an absolutely incredible number, because realize that the visible universe is estimated that to have about 10 to 80 atoms, and it exists less than 10 to 11 years. So it means that even with this speed, which I think is hardly imaginable, but today's computers are able to do it, with this speed, we wouldn't be able to count to 10 to 120 after the whole existence of the whole universe. So this number is extremely, extremely high. And now what God tells if he is looking at us. Well, he says, why are you boring me with such ridiculously small numbers? Where is infinity? Imagine that whatever number you think, 10 to 120, 10 to 1,000, 10 to 1 million, you are still in the very, very beginning of the infinity. Infinity is somewhere here. And there is no possibility to imagine any step farther or half of this way. It has no sense to think about it. Because whatever number we think, we are still in this spot and not in infinity. So something is wrong with this. And Vopienka demonstrates that big numbers really behave as being infinite. The basic property of infinite ordinals is that they can be mapped one-to-one if we extend the given ordinal by 1. So alpha and alpha plus 1 have the same number of elements. Imagine, this is more or less a real example. Imagine a big hotel having 10,000 beds. And imagine that it is evening, and somebody who is very tired comes and asks that he would like to stay in this hotel. But you know, as a desk clerk, that all beds are already occupied. But if you are knowledgeable desk clerk, what you will do? You will wake up this guest, move to his bed this newcomer, and this man or woman move to next bed. Before you have to wake up the second guest, move this first guest here, and so on and so on and so on. But realize that the night has something like 8 hours only, and this procedure may take something like 30 seconds or something like that. So you cannot you cannot finish before morning. And what is the conclusion? Because if you are waking up for say 60 seconds during the night for going to restroom or wherever, you can't say that you didn't sleep the whole night. This small break plays no role. So the conclusion is that 10,001 people slept the whole night on 10,000 beds. So the conclusion is that really this mapping is realized here. It is somehow different. It is not as strict as you have heard before, but really this demonstrates that sufficiently big numbers behave as if infinite, and we don't need to go to such huge, unimaginable numbers as I presented in my previous slide. So the alternative set theory is an attempt at developing a new mathematics on the basis of criticism of some principles of the classical one. The main criticism is focused on the cardinality theory. Many cardinalities and cardinalities which are much bigger than uncountable cardinality of real numbers. So this is criticized. On the other hand, of course, the mathematics shouldn't be thrown away, and new mathematics where standing on a green meadow is established. This is nonsense and impossible. So alternative set theory is not that different from the old mathematics. And also one of the goals is to make mathematics closer to human perception of reality. Some of the fundamental concepts of alternative set theory. First of all, we should distinguish classes which are potential only and which are actual. Classical mathematics deals with sets and also, say, classes which are actual only. It means at any moment, all elements are at disposal. This is strange, especially for infinite sets, because only God can see all sets, all elements at this very moment. And we can only think that it is possible, but it is for us impossible. And it is even unnecessary, as you have already seen. Potential classes means that at the given moment, only some part of, say, given all elements that can be constructed are at disposal, but not all are at disposal at the very moment. A simple example, if somebody brings you a piece of stone and you are a sculptor, you are going to make some sculpture, and if you make one sculpture, you cannot make another sculpture. So this is only potential that very many sculptures is possible to make from a given piece of stone, but not all of them. It is potential, it is not actual. What is the set? In alternative set theory, it is a sharp class. It means that all its elements can be put on a list, and what is very essential, when speaking about set, there always does exist an ordering according to which a set has the first and the last elements. So, from the point of view of classical set theory, every set is finite. But it is not an obstacle, because we can think sufficiently big finite sets like I demonstrated, and it is enough. For mathematics, we don't need infinity because infinity is unreachable. God is laughing to us, and nothing can be done in reality. Now the question is every part of a given set, Y is some part of a given set, X, small x is a set. Is every part of a given set a set? In the definition which I had on my previous slide, if you say a set, for example, here in this room, set of people sitting in this room, for sure this is a set, because whatever part we say, we can see every element, I can touch everybody of you, so it is not a problem. But if the set is extending larger and larger, this is not true. Simply, if you have a set with, say, 1 million or 1 billion or even larger elements, you cannot say that every part of this set is a set. Typical example are natural numbers characterizing bald people. This was a good example saying that this is really, it is not true. And also realize that if somebody, for example, would bring you to a very big pile of sand and said you, try to count the number of grains, there is, say, 1,000,000,001 grains. There is no, in principle, way how to verify that this is true. Whatever method you will develop, and try to count 1 trillion, I mean 10 to 18 plus 1, you absolutely never can be sure that you didn't make a mistake. So you can only believe that this number is true, but you cannot verify this. So such a set is so big that you cannot say that any part of this set really is a set. Therefore, this is basic of the definition. What does it mean, finite set? It is defined very sharply, and no part of it can be unsharp. So we say that a set is finite if any part of it, any subclass of it, is a set. Then we come naturally to the concept of a semiset. A semiset is a class if is a such class that there does exist a set such that each element of this class, of this semiset, is at the same time element of a set. A typical example, again, in the very beginning, natural numbers representing bald people. For sure, 100,000 number, 100,000, meaning the 100,000 hair, is this set. And we know that bald people, I'm speaking always about numbers of hair, bald people are somehow included in this set. But we don't know how large is this, and it has the first element, but it has no last element. And therefore, it is a typical semiset. This can be proved on the basis of this definition, that if A is an infinite set, and its linear ordering by the assumption it must exist. And if we put the class of all elements of this set A such that the lower cut is a finite set, then it can be proved that this is a proper semiset. I forgot to say that, of course, every set is a semiset, but not the other way around. They can exist semisets which are not sets, and such semisets are called proper semisets. This idea of semisets and finite numbers is related to the notion of horizon. So horizon is a threshold which terminates our view of the world. So we are standing here, we are observers, and here this is a horizon. We know that the world continues beyond the horizon, for sure, because if you look at the horizon, you cannot believe that this is the end of the world. Simply, this must be true. And the part of the world before is determined non-sharply. Also, it is not fixed. It can move around, so we can consider another horizon which is farther than the previous one. And on the basis of that, we construct, in fact, we can consider a class of natural numbers, and this class of natural numbers is divided into two parts: finite natural numbers and infinite natural numbers. Finite natural numbers form a semiset of finite natural numbers, and this is infinite because it has no last element, and we say that it is countably infinite. But otherwise, the class of all natural numbers is uncountable. This is quite, I think, reasonable. Again, I can refer to my previous examples with 10 to 120. This is for sure infinite number. Only we pretend it is finite, but it is not. By the definition, sets containing a proper semiset are uncountably infinite. This means because in the construction of natural numbers, every natural number here contains the whole semiset of finite natural numbers, and therefore any natural number here is infinite. So here, actual classical infinity. Classical infinity is obtained if we simply add, and we never finish, and only God can finish it somewhere. So this is classical extensional infinity. Here it is called natural infinity, which goes deeply into sets. So infinity occurs on very large, otherwise classically finite sets. I, of course, will not speak about alternative set theory in more detail. Only let me turn your attention to this concept of indiscernibility relation. It is obtained as intersection of still sharper and sharper precise relations. These relations are a mathematical model of some criteria to distinguish, to discern two elements. And we can also introduce indiscernibility of rational numbers. So if x and y are rational numbers, in fact, couples of two natural numbers, and we say that their distance, they are indiscernible if their distance is smaller than a ratio of n for arbitrary finite natural number. And then we say that an x is infinitely small if it is indiscernible from 0, and infinitely large if its ratio is infinitely small. So these are things which are related to interesting theory, mathematical theory, alternative set theory, and the concept of semiset. And in fact, the paradox of heaps or Boltzmann disappears here because Boltzmann simply form a semiset of all finite numbers, or not all, but say sub-semiset of finite numbers, and that's it. So we have finite numbers, in this case Boltzmann, and infinite numbers like everybody of you who has infinite number of hair on his head. Now about mathematical fuzzy logic, which is another theory which is able to model the phenomenon of vagueness, and the principal concept is the concept of fuzzy set, which I have already mentioned. It is a special many-valued logic which provides means for modeling various aspects of vagueness phenomenon using degrees of truth. I have already said that. And I will, at the end of my talk, show you how this mathematical logic can model this vagueness, this Sorites and Falacros paradoxes. This is only proclaim well-established sound formal system. It is capable of explanation of modeling of phenomena in which vagueness plays a significant role, and it has many well-justified applications. I can demonstrate that this is really true. There are, of course, two levels of mathematical fuzzy logic, a propositional one, then first order predicate fuzzy logic, and higher order fuzzy logic. It is called fuzzy type theory because higher order non-classical logic. It is called type theory, was established by Bertrand Russell in the beginning of 20th century. So type theory, higher order logic, does exist already more than 100 years, and its fuzzy version has been established in, say, this century. First, about structure of truth values. I think everybody knows these tables, but notice these formulas. This junction can be obtained by any of these three operations, the same thing here. Similarly for conjunction, using any of these three operations, we obtain this truth table. Equivalence and negation, I think it doesn't need to be explained. And so in fuzzy logic, we consider structure of truth values to be so-called residuated lattice. It is a lattice which is bounded from below and from up. So 0 is the smallest element and 1 is the largest element. And there is one more operation which is called multiplication. There is one most canonical, and I would say the best example of residuated lattice. It is called standard Lukashevich MV algebra. And it has the support, the interval of reals from 0 and 1. These operations are maximum and minimum. And this operation, it is called Lukashevich multiplication. And notice that this is exactly, exactly this operation. So similarly, implication, it is this operation defined using this formula. I don't have it in these slides, but simply this operation of multiplication and implication are adjoint in a certain sense. We say that it is adjoint couple, and this is residuation with respect to this multiplication. Here are other operations. Notice also this operation, it is usually called Bas delta. And what is doing, it is pushing all truth values which are below 0 to below 1, I mean, to 0. Another example is standard product algebra, but there are very many of them. But this in red one, Lukashevich one, is most distinguished and the most proper for modeling vagueness phenomenon. We can introduce fuzzy equality. It is a binary fuzzy relation. It means it is a fuzzy set in Cartesian product of two sets, which has these three properties. These are generalization of classical equivalence. Notice here transitivity. Here is this square brackets means truth value. So you should understand this as a truth value that x is equal to x. This is always 1 symmetry, and this here is multiplication. So if the degree in which x is equal to y and y is equal to z, then multiplication of these degrees is smaller than or equal to degree that x is equal to z. Higher order fuzzy logic. I don't have time to speak about it in detail. It would take me several hours. But the idea is to formalize reasoning with objects of arbitrary kind. It means in propositional logic, the basic object is proposition, which is represented modeled by truth value. In predicate logic, we speak about predicates. It means about relations among elements of arbitrary kind. It can be numbers, people, tables, whatever. And in higher order fuzzy or higher order logic, not only fuzzy one, we can speak about arbitrary objects. The essential concept is the concept of type. The type you should understand as a sort of subscript or index which characterizes the kind of objects. So we have two elementary types, the truth values, this is Greek omicron, and epsilon objects. And then we form from them iteratively types of higher order. You will understand surely what does it mean. Formulas have always a type. So if A is a formula and alpha is a type, then A alpha is a formula of type alpha. And if, for example, we have A alpha and A beta, it should be understood as two different formulas. So type is uniquely assigned to any formula. And then this is iterative definition of how formulas are defined. And notice this formula. This is so-called lambda formula, or sometimes you can see also the term lambda term. It should be understood as a sort, I say always, materialization of a function. It means that it represents a function which to every value of this variable x alpha assigned variable a value of type beta, some element of type beta, obtained from this formula A if we replace value of this variable x alpha inside this formula A beta. Here this is important because here function is not necessarily understood as a relation between two sets. It can be also understood as a procedure, and for example these lambda terms, these expressions are quite often used in computer science for characterization of running programs or structure of programs. This fuzzy type theory has inference rules. This R inference rules is a sort of equivalence rule where if we have two equivalent formulas, then in another formula we can replace one occurrence of one formula with the another one. And this it is corresponds to application, if you remember this Bus delta simply formula which for unit stands and everything which is smaller than unit tends to zero. The concept of axioms, fuzzy equality and so on, the concept of proof is classical probability. We say a formula is a provable. It must be formula of type truth value. It means proposition. If there does exist a proof of it, and a theory is determined by a set of special axioms. Some more complex formula are formed using connectives, disjunction, conjunction, also strong conjunction. So notice that in fuzzy logic we have two conjunctions and in fact two disjunctions also. One conjunction is modeled using infimum operation or mid operation in lattices, and the other one is modeled by multiplication. Because if you remember my slide with Boolean algebra of truth values and these formulas, we can say that there does exist only one logic, and this is fuzzy logic. And classical logic is only a very special case of fuzzy logic. So in every logic we have more than one conjunction, but in classical logic these two conjunctions coincide. The same for these junctions. Of course, quantifiers and this Bus delta and so on. To understand it better, let me say a few words about interpretation. So interpretation of higher order fuzzy logic is done in a model. It is a system of sets of all kinds of types. And on each set, fuzzy equality is defined. And of course, a certain algebra of truth values. Essentially, this can be this Lukashevich MV algebra, but there are, as I said, many other algebras which can be considered. And then the model, it is this system. So here it is depicted in a more transparent way. This is a set of truth values, which is in fact a support of this algebra. And the fuzzy equality here is equivalence. And then we have some set of elements. It means set of elements having certain property and certain fuzzy equality. Then from this we construct some set of functions on truth values, some set of functions from elements to truth values. Notice the reverse order of types. So these are functions from elements to truth values. And of course ordinary functions and so on up to infinity. So I think this is quite clear, and on the basis of that we can have interpretation of formulas. It means If A is a formula of Omicron, of type Omicron, it means a truth value, a proposition, then its interpretation is some element from the set of truth values. Similarly here, if it is a formula of type epsilon, then its interpretation is an element, arbitrary element. If it is a formula of type gamma beta, then its interpretation is a function from a set of type beta to a set of type omega gamma. As a special case, fuzzy sets are functions from a set of type beta into truth values, and so on and so on. Concerning the connectives, fuzzy equality in syntax is interpreted by a truth value of fuzzy equality between these two elements. Disjunction, it is an operation of join. Conjunction, operation of meet. Strong conjunction is an operation of multiplication. And then implication, Bars delta, negation. And notice quantifiers. The general quantifier is interpreted as infimum of all truth values obtained by all instances of this formula over all elements over a given type. And here it is a supremum of these truth values. So this is very essential and a very well working definition. And the completeness theorem can be proved, generalized completeness of this fuzzy type theory. Arbitrary theory is consistent if and only if it has so-called general model, or simply model, forget about what does it mean general. And for every theory T and a given formula, a formula is provable if and only if it is true in all models in a degree 1. So we have probability, and probability means true in a degree 1. But of course, we can have formulas which in a given model have truth value which is smaller than 1, arbitrary 1. But then we cannot speak about probability of such a formula. It has only some truth values, and probability concerns only truth value 1. And now I will return to Fallacross and Solitas paradoxes in fuzzy type theory. Let me mention that there does exist a very important part of expressions of natural language. These expressions are called evaluative linguistic expressions. Here are examples: small, very small, rather medium, quite shallow, roughly big, very intelligent, beautiful, and so on and so on. These are from three constructed from three expressions of the kind small, medium, and big, and by some linguistic hedge. These are examples of linguistic hedges. And in fact, interpretation or the meaning of such expressions is in principle the same as the meaning of expressions bold or heap in my first example. In using this fuzzy type theory, we can model semi-set of finite natural numbers by a certain fuzzy set of small numbers. So we construct a formula which represents and whose interpretation is small or very small, and all these expressions. And in fact, this can be taken as approximation of a semi-set of finite natural numbers from alternative set theory. Notice one essential thing. While alternative set theory deals with mathematical objects which are of new, slightly different kind, fuzzy sets and fuzzy logic stays inside classical logic. We have classical sets, also classical infinity, and so on. So this is a really different model of vagueness phenomenon, but it is related to ideas of alternative set theory besides others by this. Notice that these expressions, especially these relative expressions, and also say boldness and heaps and so on, are related to context. Context here for these expressions can be understood as a scale which is characterized by three numbers or three elements. the left bound, the smallest element, right bound, the largest element, and some typically medium value, which can be on arbitrary place in this scale. So this idea of context relates to the real life, because we use the same words, say small, in very many contexts. We can speak about small people, we can speak about small buildings, we can speak about small beetles, we can speak about small planets, small stars, and so on. In each case, we speak, in fact, concerning the values. Small star, for example, sun is a small star, 1,300,000 kilometers in diameter. And small beetles can be something like 3 millimeters. Still, the essential meaning of this expression small is the same. And this is the idea of this model. So the context is really important here. In this fuzzy logic, the context is a special formula of this type. There are good reasons to define it like this. Here, consider the left bound to be 0, right bound to be some value q, and some central, typically medium value is denoted by p. And this is a formal theorem based on axioms of a special theory of these evaluative linguistic expressions. I didn't present them, but they do exist, believe me. So any man or woman with 0 hairs is bald in any context. This context is always here. Whatever number bigger than this typically medium number means not bald. It means that really do exist people who are bald and who are not bald. So you can be happy. There does exist borderline number of hairs, which means partially bald. This is a formula. Here is special operator, special connective, which means that this formula has non-zero truth degree, the truth degree between 1 and between 0. In any context, there is no number of hairs surely bald, and such that n means surely bald, and n plus 1 surely doesn't mean bald. In other words, there is no abrupt change. The continuity here is preserved in this formalism. This is very important. And characterization, what I said, that if somebody has, so for example, 100 hair and somebody has 100 plus 1, then they are slightly different. So this essential implication, which was in my first slide, for all n, bold n implies bold n plus 1, is here not accepted, but it is replaced by such a formula. And here, this characterizes this change of shape between n and n plus 1. This is a certain indiscernibility or relation, fuzzy equality. And in fact, this formula means that bold n plus 1 is almost true, but not precisely true, not true in a degree 1. So if somebody is bold, then it is almost true that n plus 1 is true, is bold, but not true in a degree 1, as I said. Similar theorem can be proved also for other properties, small, big. So here is essentially the same theorem like previous, only somehow other way around. It means that the largest value, q, is big, and so on and so on. I think it's not necessary to read it in precisely. So you can see this formula are in principle the same. So the mathematical model or semantics of small and big are very similar, and they solve the Sorites or Fallacross paradox. Also, this can be extended not only to natural numbers, but arbitrary numbers. So such a theorem can be proved that there is no last surely small x and no first surely big x. So the continuity does hold only for natural numbers, as in my previous theorem, but also in the if we consider, as I said, real numbers. Simply, for example, if you consider a bottle which has little water inside, So you cannot say that this bottle is almost empty, and if you add 1 milliliter, then it is already very full. Simply, this abrupt change does not exist here. So I am close to the end. What I tried to demonstrate, to persuade you about is that the Phalacros and Sorites paradoxes reveal that there are properties for which the induction principle doesn't hold. So, let me emphasize that these are only examples of two simple properties. But if you think about semantics of natural language, about words which have full meaning, then you realize that absolutely most of them are vague. The semantics of such expressions of sentences is vague. So properties which don't allow to be modeled using set theory are prevailing. Only very, very few, exceptionally, they can be modeled using sets, but are otherwise not. Vagueness is related to concept of infinity of the alternative set theory, the infinity which is called here natural infinity. A higher order fuzzy logic provides a model of the Phalacros and Sorites paradox. This I have just demonstrated. And the vagueness phenomenon can be modeled using the means of fuzzy type theory. Perhaps next time I can speak in more detail about that, but I think to get the idea about what is going on is captured here. So that's all. Thank you very much for your attention. Yes. 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 There are many sort of systems of fuzzy logic. I was speaking about one of them, but there are really many. And for all of them, the completeness theorem has been proved.
No questions, so I would like to say to Professor again.
Thank you.
Maybe we will find some more questions during the banquet.